So now we are on YouTube, right? Okay.
Yeah. Yeah, so we are live.
It's amazing, actually. We do like PhD defense on YouTube. It's amazing. So are we doing everything online, or are there people like attending in
No,
person?
there are some members here.
Oh, okay, okay. So are we doing everything online, or are there people like attending in person?
No, there are some members here.
Oh, okay, okay.
Yeah, actually, you're all here because
are we doing everything online, or are there people
no, there are some members here.
Oh, okay.
C'est toi l'écho? Ah mince. Il y a un écho là. Oh, je sais pas. I don't know. So yeah, we are waiting here for Xavier, Marc, Huiling, and Rajendra. And you four are here, so as soon as they are here, we go here because can you hear me? Can you hear me well or not? No. Il y a un écho là.
Jan? There is an echo with a long delay.
Yeah, I don't know. So yeah, we are waiting here for Xavier, Marc,
Yeah, that won't work.
And you four are here, so as soon as they are here, we go here because can you hear me well or not? No. Okay, we're trying to solve the problem. Do you hear an echo now? Tu penses que c'était le... Bonjour. Bonjour à tous. On entend bien? So we're waiting for the jury members who are still having lunch. So. The jury members are here, so we're gonna start shortly. Alors, je passe sur le micro. Comme tu veux. Oui. Comme ça, on garde le.
So good afternoon, everyone. Welcome to the PhD defense of Yann Thanwerdas. So the jury has selected a president who will be the master of ceremony for this PhD defense. And the president is Rodolphe Sepulcre, and I will leave him the duty to present the jury and lead the the whole event.
Thank you very much, Xavier, and welcome to everyone. This is the public PhD defense of Yann Thanwerdas. And the jury, we have a very distinguished set of international experts to evaluate the thesis. So I will briefly introduce them. First, we have two rapporteurs. So the first one is Pierre-Antoine Absil, who is professor at the Université de Louvain in Belgium, and Professor Marc Arnaudon from the University of Bordeaux. And then we have external examiners, including two of them in person. So Professor Rajendra Bhatia, who is currently professor at Ashoka University in India. And then Professor Willing Lay, who is emeritus professor at the University of Nottingham. And then we have three members online, starting with Min-Ha Kwang, who is associate researcher at the RIKEN Center for the Advanced Intelligence Project in Tokyo. Frank Nilsson, likewise from Tokyo, researcher at Sony. And myself, professor of engineering at the University of Cambridge. And of course, last but not least, the supervisor of the thesis, who is Xavier Pennec from INRIA at Sophia Antipolis, who is in person and was just speaking a minute ago. So without further delay, we'll now hear the presentation of Yann Thanwerdas. You have about 45 minutes to explain the main outcome of your PhD. Thank you.
Thank you, Mr. President. So let me just start the presentation. Yeah. So yeah, I would like to thank all the jury members for being here or for following us remotely. Thank you, Mr. President, for the introduction. So my name is Yann Thanwerdas, and I'm going to present to you my PhD work that I did during my PhD thesis, which was supervised by Professor Xavier Pennec, and which is entitled Riemannian and Stratified Geometries of Covariance and Correlation Matrices. So this is quite a few strange words. So what are covariance and correlation matrices? Where can we find them? And why do we need to care about their geometry? So for example, covariance matrices can be found in diffusion tensor imaging. Diffusion tensors are 3D symmetric positive semi-definite matrices, which contain the diffusion coefficients of water molecules in the brain. They're represented by 3D ellipsoids, and the longest axis of the ellipsoid indicates the main direction of diffusion. In electroencephalography, we can compute the covariance between two signals collected at two electrodes on the brain. And all these covariance coefficients form a matrix that is called the covariance matrix. We can also compare the correlation coefficient, the correlation between two signals independently from their scales. So the correlation coefficient is the covariance normalized by the standard deviation of the two signals. And that's why they are between -1 and 1, as you can see on the correlation matrix here. And so the correlation matrix is the set of all correlation coefficients all together in a matrix. So for example, here, it's a correlation matrix between brain regions in functional MRI. And it can also model other types of correlations between electrodes, between genes, cells, or amino acids, for example. So more precisely, how do we compute a covariance and a correlation matrix from raw data? So given a set of signals, we can sample the signal and remove the mean. We get this matrix X. then multiply by the transpose. So we get the covariance matrix, sigma. And then we normalize by the standard deviations, and we get this correlation matrix, C. And so we can already observe that in the covariance matrix, there are n times n plus 1 over 2 free coefficients where n is the dimension of the matrix, because the matrix is symmetric. And in the correlation matrix, we have only n times n minus 1 over 2 free coefficients, because the diagonal is fixed to 1, to identity. And these the positivity constraints on covariance and correlation matrices make these spaces non-linear. So the space of covariance matrices is a convex cone, a closed convex cone in the vector space of symmetric matrices. And symmetric positive definite matrices, or SPD matrices, are located in the interior of the cone. So they form an open convex cone. And since it is open and convex, it is diffeomorphic to the vector space of same dimension, n times n plus 1 over 2. And so here is represented the cone of 2D covariance matrices. The set of correlation matrices is a compact convex set in the vector space of symmetric matrices. It's also compact and convex in its affine span, which is the affine space of symmetric matrices with identity diagonal, which is denoted here identity plus whole n, where whole n is the vector space of symmetric matrices with null diagonal. And so the full rank correlation matrices are located inside, so in the interior of the ellipto. This space is called the ellipto. And so they form an open convex set in the affine space of symmetric matrices with identity diagonal. And since it is open and convex, there exists a diffeomorphism towards the vector space of dimension n times n minus 1 over 2. And so here is the set of 3D correlation matrices. And so these spaces are not vector spaces. So covariance and correlation matrices belong to the family of nonlinear data, as well as trees, meshes, candle shapes, for example. For example, the set of phylogenetic trees is an orthon space. The positive orthont in a vector space is the set of vectors with all positive coordinates. And so an orthon space is a set of orthons glued together in a certain way. So the question is, how can we compute in these spaces? For example, how can I interpolate between two trees in this space? How can we define probability distributions on the spaces of covariance and correlation matrices? And so to answer all these questions, we need to formalize a bit more the spaces we will work in. So I will talk about three types of spaces: the vector spaces, the manifolds, and the stratified spaces. A vector space is a space that is stable by addition, difference, and scaling. A manifold is a space that can be locally approximated by a vector space called the tangent space at each point. So for example, vector spaces are manifolds, trivial examples of manifolds. Open sets of vector spaces are also manifolds, such as the set of positive real numbers or the set of SPD matrices. And we can also cite the famous example of the sphere, which is a manifold. And then a stratified space is a set of several manifolds glued together in a certain way. For example, the space of non-negative real numbers is a stratified space because it is composed of two manifolds, the manifold of positive numbers and the trivial manifold with the zero, with only zero. And so the cube and the spider are also examples of stratified spaces. So let me develop this idea of stratified space on the cone of covariance matrices. So the cone of covariance matrices is a stratified space with 3 strata. The first stratum is composed of the 0 matrix, the only matrix of rank 0. Then we can add the matrices of rank 1, and we get the boundary of the cone. And then we can add the rank 2 matrices, the SPD matrices, and we get the interior of the cone. And so we get the whole space of covariance matrices, 2D covariance matrices here. And so the space of SPD matrices is dense in the space of covariance matrices. So how do we generalize the classical linear operations from Euclidean spaces to these other nonlinear spaces? Euclidean geometry is based on the choice of an inner product. For example, the gradient changes if the inner product changes. On a manifold, the analogous basic geometric operation is the Riemannian metric. It is an inner product on each tangent space. And so many Euclidean operations can be generalized to Riemannian manifolds, such as the geodesics, the gradient, the measure, and some new notions appear, such as the curvature. On a stratified space, we usually define a distance, which is a more general notion, but which conveys much less geometric operations. And so these geometric operations are the building blocks to perform statistical operations. So many Riemannian algorithms and results extend the usual ones in Euclidean spaces, as you can see here. And on the contrary, in metric spaces, there exist fewer general algorithms and results. And so on stratified spaces in the literature, the methods that are used are mainly defined specifically on examples of spaces. So now let me convince you that the geometry changes the statistics and the data analysis with 2 examples. So on the left, you can see the regularization of a DTI slice around the corpus callosum in the brain. And so the first image is the raw estimation of diffusion tensors. The second one shows Euclidean regularization of the tensors. And the third one shows a Riemannian regularization. And you can see that the Riemannian regularization is smoother than the Euclidean one and without outliers. On the right, maybe even more striking, you can see an example of classification between left-hand movement and right-hand movement in brain-computer interfaces. And the use of a Riemannian metric was shown to separate much more accurately the 2 classes than the use of a Euclidean metric. So the geometry determines the statistics and the data analysis. However, there is not a canonical choice of a geometric structure on covariance and correlation matrices, and more generally on these nonlinear spaces. So which principles should we follow to choose the geometric structure on our nonlinear spaces? So in my thesis, I proposed 3 principles. The first principle is the adequacy of the model to the data. So for example, we can require that the geometric structure is invariant under a group of transformations if these transformations should not influence our data analysis. I will develop this later on covariance matrices. As the second principle is to have good theoretical properties with our space. So here I wrote two sequences of geometric structures such that the ones on the right have more properties than on the left. And these good theoretical properties often come with good practical properties, such as closed form formulae and efficient algorithms to implement in libraries such as geomstats to compute on nonlinear manifolds. And such requirements often define families of geometries rather than a unique geometric structure on our spaces. So I will apply all these principles to the spaces of covariance and correlation matrices. In the first part, I will focus on the manifold of SPD matrices. I will show you that there are many existing Riemannian metrics in the literature, and so I will use the previous principles to propose a classification of these Riemannian metrics into families with general properties. In the second part, I will turn to the manifold of full-rank correlation matrices. And here there are very few existing Riemannian metrics in the literature. But we saw previously that this space, so the interior of the ellipto, is diffeomorphic to a vector space. And so I will propose several diffeomorphisms towards vector spaces to define log Euclidean metrics on full-rank correlation matrices. And in the third part, I will focus on the stratified space of covariance matrices. So the pure Wasserstein distance is defined globally on this space, but it was only studied on each stratum, and so I will give you the global picture. So let's start by classifying Riemannian metrics on SPD matrices. Let me show you that there are many Riemannian metrics, and then we'll use, I chose two principles for this presentation to classify these Riemannian metrics. So until 2005, 2006, the Euclidean metric was the one that was mainly used in applications to classify covariance matrices or to do operations with covariance matrices. And the affine invariant metric was shown to outperform many classification results and was better suited to compute with covariance matrices. Then the log Euclidean metric was proposed as another alternative, and then there was an explosion of proposals on the Riemannian metrics that we could use on SPD matrices. So maybe a first element of classification is to note that almost all of them are invariant under the action of the orthogonal group. So I will explain what it is. And so first, I would like to present the four main metrics: the Euclidean, the affine invariant, the log Euclidean, and the pure Wasserstein metrics on SPD matrices. So we can see that they are different from the formulae of their distances, Riemannian metrics, and the formula of the mean. And so to give some intuition, the affine invariant metric and the log Euclidean metric reject all the rank deficient matrices to infinity. So these matrices are not reachable from SPD matrices. On the contrary, the pure Wasserstein metric keeps these rank deficient matrices at finite distance. And so that's an important difference between them. And so you can see an interpolation between two covariance matrices, SPD matrices, with the four Riemannian metrics. And you can see that they give different results on this interpolation. So let's apply our first principle, the invariance under group action. So the natural action on covariance matrices is the congruence action of the affine group which reduces to the covariance action of the general linear group. It comes from the action of the affine group on random vectors. And so then when we look at what it gives on the covariance matrix, we get this formula with A sigma A transpose. And so all the affine invariant metrics were characterized by this formula with two parameters. They endow the space of SPD matrices with a Riemannian symmetric structure. The singular matrices are rejected to infinity, and we have closed form formulae for all the geometric operations. And so a natural question is to try to characterize the metrics that are invariant under subgroups of the general linear group. So here are several subgroups of the general linear group. And so, for example, if we require that our geometry is invariant under permutations, it means that we don't that the order that we chose between the entries is arbitrary. So this diagram is quite easy to obtain from these subgroups, the inclusions and intersections. And so each group defines a family of Riemannian metrics that are invariant under this group. So here is the first theorem saying that all permutation invariant metrics that are also invariant under the group of lower triangular matrices with positive diagonal are invariant under the general linear group, so are affine invariant. I also characterized the continuous O of n invariant matrix and the LT plus invariant matrix that's detailed in the manuscript. So let's turn to our second principle, the principle of dually flat manifolds. A dually flat manifold is a Riemannian manifold equipped with two flat torsion-free connections, nabla star, that satisfy a condition of duality with respect to the metric. And so this geometry is very interesting because it provides a canonical Bregman divergence. A divergence is a dissimilarity measure that looks like a distance, but without the symmetry condition and the triangular inequality condition. And so we can generalize the notion of mean into the notion of centroids. And with this dissimilarity measure, we can perform some operations that we can do with the distance, such as clustering. So maybe an example on divergences, the Kullback-Leibler divergence is probably one of the well-known divergences. So here on the set of positive vectors, so actually behind the Kullback-Leibler divergence, there is a dually flat manifold structure with the metric written here and the two connections, the Euclidean and the log Euclidean connections. And so this Kullback-Leibler divergence belongs to a more general family, the family of alpha-beta divergences. So if you take alpha equals 1 and beta tends to 0 in this formula, you will retrieve the Kullback-Leibler divergence. And so these alpha-beta divergences, they can be defined also on SPD matrices. And so behind these divergences, there is a dually flat manifold structure. And so I defined the mixed power Euclidean matrix as the matrix corresponding to these divergences. And the interesting point with this family of metric is that it encompasses many Riemannian metrics that we saw before. For example, the Euclidean metric, the affine invariant metric, the log Euclidean metric, and many others. So it gives some structure to the set of Riemannian metrics on the manifold of SPD matrices. I derived the formula of the curvature. I proved that there is always non-positive curvature, and I proved experimentally that there is always non-negative curvature with all these metrics. So to summarize, I characterized several classes of invariant metrics with respect to the group of invariants. I defined these mixed Euclidean metrics that are a bit more general than the mixed power Euclidean metrics. And I derived the curvature for all these metrics. And so this gives a hierarchy of families of Riemannian metrics. And each time you know some general operations in a family, you can implement it. And as soon as you know a better way to compute for example, the curvature, you can specify a more efficient algorithm. And so this gives a hierarchy of implementations in libraries such as geomstats. Another observation is that the Beer-Wasserstein metric that I mentioned previously does not fit in this framework of mixed Euclidean metrics. And so I will explain it more precisely in part 3. So these works gave rise to several publications that are written here. So now let's turn to the manifold of full rank correlation matrices. So we go from covariance matrices to correlation matrices. I will show you that there is very few metric, and so I will develop this quotient affine metric that was defined actually during my thesis. And then I will define some other metrics that are more convenient, that are called log Euclidean metrics. So the quotient affine metric was introduced by Paul David in his thesis. So the space of correlation matrices can be seen as the quotient of the space of SPD matrices by the positive diagonal group, because we said that the correlation matrices are normalized versions of covariance matrices. And so any Riemannian metric that is invariant under the positive diagonal group on SPD matrices descends to a Riemannian metric on full rank correlation matrices. So they defined the quotient of the affine invariant metric that I called the quotient affine metric. And I derived all the formulae that were not derived in the original work, such as the Riemannian metric that you can read here. And so from this work, I could derive some properties of this metric. So it's a quotient Riemannian metric. It is geodesically complete because the affine invariant metric is geodesically complete on SPD matrices. It is invariant under permutations, and it is also core inverse consistent. The core inverse involution is what we would like to define as an inversion on correlation matrices. So if we inverse a covariance matrix, we get what we call, sorry, I'm missing the word. I cannot hear. No, I'm sorry, it will come back. Precision metrics, thank you. that's why we have an advisor. So, the precision metrics, and so on correlation matrices, the equivalent is the core inverse involution, because the inverse of a correlation matrix is not a correlation matrix, and so we have to renormalize. And this core inverse matrix contains the partial correlations up to a sign. And these partial correlations are very important in several fields, such as stationary stochastic processes or Gaussian graphical networks. And so I think that this property of inverse consistency is very important. So on this quotient affine metric, I derived the formulae of the geodesics and the curvature. So you can see that the formula is quite ugly. And especially in the formula of the curvature, there is a negative term and a positive term. So it was a bit difficult to determine the sign of this curvature. And so I proved that it's not of constant sign and that it is unbounded from above. It means that we can find a sequence of correlation matrices such that the curvature tends to infinity, plus infinity. And so this is not very convenient because we said that this space of full rank correlation matrices is diffeomorphic to a vector space. And so it's not convenient to have a curvature that is unbounded and not of constant sign. So I would like to define diffeomorphisms towards vector spaces that preserve the good properties of the quotient affine metric without the drawbacks. So I proposed here 3 families of such metrics. The 2 first ones are adapted from works that were done on SPD matrices. Maybe we can do the pointer. The adaptation is to renormalize by the diagonal here and here. And so we get a diffeomorphism from full rank correlation matrices to a space that we can Euclideanize quite easily, either by removing the identity or by taking the matrix logarithm. These 2 metrics are not invariant under permutations, and they are not inverse consistent. So I wanted to find alternatives. And so I found quite recently this work from Arshakov and Hansen, who defined a bijection from full rank correlation matrices to a vector space. And I proved that this log here is actually a diffeomorphism. And so since it is a diffeomorphism, we can pull back the inner products on hollow matrices, symmetric with no diagonal. We can pull back the inner products and define log Euclidean metrics on full rank correlation matrices. They are permutation invariant, but they are not inverse consistent because here we remove the diagonal after taking the logarithm. And so this is not compatible, this linear operation is not compatible with the congruent action of diagonal matrices on SPD matrices. So what could be an alternative? We shouldn't take the logarithm because here we are quite obliged to remove the diagonal. So I tried to find another path. And I realized when I studied the permutation invariant inner products on the vector space of symmetric matrices that we can decompose the space of symmetric matrices with another space that is this row 0, the space of symmetric matrices with null row sums. So this is a direct sum. And then the exponential of this space is exactly the manifold of SPD matrices with the unit row sums. And so we have 3 spaces that are in bijection with this matrix logarithm. And so the last question is, can we decompose SPD matrices as a positive diagonal matrix and a matrix in row 1 plus? The answer is yes. It was given by Marshall and Olkin in '68. It's called the scaling. So for all SPD matrices, there exists a unique positive diagonal matrix such that the congruence up to D of this SPD matrix is in a row 1 plus. And so we have this decomposition of SPD matrices. So now we can go from correlation matrices to row 1 plus by simply taking the scaling, and we get a diffeomorphism from the full rank correlation matrices to this vector space rho 0. So I proved that this is a diffeomorphism, it is permutation invariant, and it is core inverse consistent because the space rho 1 plus is stable by inversion. And so the inversion corresponds exactly to the core inversion on correlation matrices. And so we preserved this property from the quotient affine metric. So we have the good properties without the drawbacks. So to summarize, I computed the geometric operations of the quotient affine metric. I defined 4 families of log Euclidean metrics on full rank correlation matrices with interesting invariance properties. And so this provides simple principled metrics to compute with full rank correlation matrices. And so these works also gave rise to several publications. So now I will go to the third part, the Biot-Wasserstein orbit space of covariance matrices. So I will present briefly the works on geodesics in each stratum, and then I will explain you what are the geodesics in the total orbit space. So in contrast with log Euclidean metrics, these metrics are not complete. The geodesic is not unique between 2 points a priori, and the geodesic needs not be globally minimizing. And so we need other notions to characterize the minimizing geodesics, such as the definition interval, the set of pre-images, and the cut time. That allow, so if we want to characterize the minimizing geodesics, we need to characterize these notions. So here is a summary of contributions of many researchers on this field, on the Biot-Wasserstein metric. My contributions were especially to compute the cut time in the main stratum of SPD matrices and in other strata. And it came from a problem that we had in geomstats when we were computing the logarithm of the exponential, the Riemannian logarithm of the Riemannian exponential. We were not retrieving the initial tangent vector, and it was coming from the fact that we were shooting too far. So now we know the cut time, and we know what we are allowed to do actually. So now I will briefly present the concept of Riemannian orbit spaces to explain the example of the Biot-Wasserstein orbit space. So as defined by Alexevsky and colleagues, a Riemannian orbit space is a Riemannian manifold is based on a Riemannian manifold on which we have a group action that is smooth, proper, and isometric. And we are taking the quotient of this space. So we can compute the orbits, and we can show that the orbits are exactly the covariance matrices. And so the orbit space is the space of covariance matrices. Then we can compute the isotropic group, also called the stabilizer. And we can prove that 2 points have conjugate stabilizers if and only if they have the same rank. And so we will retrieve the stratification by the rank of covariance matrices. So first of square matrices, and then of covariance matrices. So the strata, the stratum of a matrix sigma is the set of all matrices that have the same rank. And so now we can characterize all the minimizing geodesics between any 2 covariance matrices independently from their ranks. So a first property of orbit spaces is that on the minimizing geodesic, we cannot meet a more singular orbit. And so the direct consequence of this fact is that any minimizing geodesic is of constant rank on the interior of the segment. And thanks to the structure of the Riemannian orbit space, we can prove that they are parametrized by this matrix R, that is an orthogonal matrix satisfying this condition: X transpose Y R transpose is a positive semi-definite and symmetric, where X and Y are defined like this, such that XX transpose is the first point and YY transpose is the second point. The problem is that this parametrization is not injective, so we cannot count the geodesics based on this parametrization. So I wanted to find an injective parametrization. And so if we take the same notations, sigma 1, sigma 2, and xy, and we denote k, l, r, their ranks, without loss of generality, we can assume that the n minus k columns of x and the n minus l columns of y are null because of the right action of the orthogonal. And thanks to this action again, we can also, without loss of generality, assume that the product X transpose Y is a diagonal matrix. And thanks to these simplifications, we can now simply characterize the matrix R that we had on the previous slide. And so the matrix R has to be of this form, with an identity block and an orthogonal block here. And so this matrix composed with R0 and R1 belongs to a Stifel manifold. And the fact is that the dimensions are such that the matrix R0 is unconstrained in the closed unit ball for the spectral norm. And so now, if we compute the geodesics thanks to the previous formula, we can see that only R0 has an impact on the geodesics. So here is the new formula, parameterized by R0 in the closed unit ball for the spectral norm. And now, this is an injective parametrization with R0 appearing here. And so since it is injective, we can now count the number of minimizing geodesics. And so the geodesics, the minimizing geodesics, there exists a unique minimizing geodesic if and only if the rank of the product R equals one of the two ranks. So here L, because it was supposed to be inferior to K. In particular, when K equals N, the geodesic is unique. It means that when we take two matrices and such that one of the two is invertible, there is a unique minimizing geodesic from an SPD matrix to any other covariance matrix. Otherwise, when R is not equal to L, there is infinitely many minimizing geodesics between the two covariance matrices. And there is an interesting choice for R0, which corresponds to 0. And this choice leads to a canonical expression that reduces to be the unique one when there is a unique one. And so this formula implies the pseudo inversion denoted dagger here. And so it's a closed form formula between of a geodesic, minimizing geodesic between two covariance matrices that is independent from any choice of X or Y and independent from the ranks K, L, and R mentioned previously. So to summarize, I gave some compliments on the geodesics in each stratum of covariance matrices. And I gave the expression and the exact number of minimizing geodesics in the orbit space of covariance matrices. So this allows to interpolate between covariance matrices of different ranks. And this gives a pedagogical example of geodesics in a Riemannian orbit space. And so I hope this will allow to compute other minimizing geodesics in other spaces, such as the space of correlation matrices. And so this work gave rise to this submission in SciMax. So to conclude, on the manifold of SPD matrices, I gave some compliments on the curvature of the affine invariant metric and the parallel transport of Purva-Sorstein metric that I didn't present here, but that are detailed in the manuscript. I proposed the elements of classification of Riemannian metrics, and I characterized the continuous O of n invariant metrics. And I defined this family of mixed Euclidean metrics that I related to the alpha beta divergences, and for which I derived the curvature. On full rank correlation matrices, I computed the geometric operations of the quotient affine metric, and I proved that the curvature is unbounded, and this led to introduce other metrics that are log Euclidean, and especially a family of permutation invariant, co-inverse consistent log Euclidean metrics. And on the orbit space of covariance matrices, on the stratified space of covariance matrices, I took this Purva-Sorstein distance and I gave some complements in each stratum, and I characterized the minimizing geodesics of this distance. So this gave rise to several publications or submissions in conferences and journals. And so I would like to give some perspectives to this work. So I think that it would be worth to apply all this to several research domains, such as genetics, connectomics, electroencephalography, and many others. And I think that these product metrics on covariance matrices are composed of a part on the scaling and a part on the correlation are quite promising, because they are completely different than all the metrics that were used on covariance matrices. We proved that the correlation coefficient is interpolated monotonically with these kind of metrics, which is not the case with all the metrics that were used until now. So if the correlation is important in the application, it should give interesting results. I would also like to transpose the work I did on covariance matrices, on the Purva-Sorstein orbit space of covariance matrices, to correlation matrices. The space was already described, the geometry of the space, but not the geometry of the distance that we can put on it. So I think it would be interesting to derive all the formulae, or to compute them numerically. I think that we can also relate some other works to these works, especially the works on spaces of matrices of any size and any rank, because it was only done, from what I know, on Grassmannians and SPD matrices, and I think it could be transposed to PSD matrices, to semi-positive definite, positive semi-definite matrices, because we can a PSD matrix is represented by a cylinder, or a rank deficient matrix, and so I think it could be generalized. And I also worked on permutation invariant and block orthogonal invariant inner products, and I think this could relate to the stratification by eigenvalue multiplicity and the works on flags. So interesting to work on this. I would like to sincerely thank my supervisor, Xavier, and many other people that I will probably have the opportunity to thank later. Thank you for your attention, and I'm open to any question and comment. Thank you.
Thank you very much, Yann. Perfect timing, and I wish I've had this presentation before reading the dissertation, because you very nicely highlighted the important contributions. So it was extremely clear, in my opinion. So now the members of the jury will have an opportunity to ask a few questions, and we will start with the two rapporteurs. And so the first one being Pierre-Antoine Upsil from the University of Louvain. So please, Pierre-Antoine.
Thank you. It was a great presentation indeed. So the thesis is very deep, many contributions. So I thought you would have to focus on some aspects, but in fact, you were able to give an overview of the whole work. So that's really impressive. I said many nice words about the thesis in my report. So I will go, I really like it. It's an impressive work. I will go straight to a few questions. So we had some discussions about details some time ago. So my questions now are more high level. But okay, so when you reach the green part of your presentation, so the part 2 about the correlation matrices.
Excuse me, I just interrupt you. I'm sorry.
Yes.
I'm just trying to see your face on the screen because I'm not able to see you. So
okay, so I see myself at least. So
okay,
my camera should be on.
So I'm just trying to see you because otherwise it's more difficult to understand.
Maybe you could stop sharing.
Yeah, I stopped it, but then
okay.
I think I thought when I would try again, your faces would reappear, but actually, okay. En fait, comme je les ai mis en bas, elles ont disparu.
I don't think we need the slides for the discussion, so I think you can just stop sharing.
Okay,
no, it will be okay. Yeah, I was going to ask some things that relates to a slide, but I don't need to see the slide for my question. No, it's not needed.
Okay. Well, okay. Okay, sorry. So now I can see you.
Okay. So when you start discussing these full rank correlation matrices, right away you want to go for the quotient of the SPD manifold, quotiented by the congruence action of the positive diagonal matrices. But maybe another approach would be to just consider the set of full rank correlation matrices as a submanifold of the SPD manifold. And then whenever you have a metric on the SPD manifold, you induce a metric on the submanifold. So what would you think about that approach? Would it be too hard to say anything clever about these geometries of the correlation matrices? Or would you lose some key properties or whatever? What do you think about that idea?
So yeah, it's true that whenever we have a Riemannian metric on a manifold, we can look at the Riemannian metric on a submanifold, the induced Riemannian metric. And so it was a bit studied, especially if we take the affine invariant metric that is also called the Fisher-Rao metric. Nielsen looked at it. And they proved that the manifold of full rank correlation matrices is not totally geodesic submanifold for this metric. And I think that we can easily prove, I think I wrote it in the manuscript, but I didn't properly prove it, but I think it shouldn't be too difficult to prove that it's also true for the log Euclidean and the Biot-Wasserstein metric that the set of full rank correlation matrices is not totally geodesic subspace. The problem with these induced Riemannian metric is that we cannot say many things on the subspace. So for example, we can compute the curvature. I think it's a formula from Cartan. Cartan and someone else. I don't remember. Gauss-Codazzi the equations, I think. So we can compute the curvature, but for example, we cannot compute. We don't have a generic way to derive the geodesics, so we can compute them numerically. And so, of course, probably we could do everything numerically. And actually, in GeoStats, I think we have all the tools to compute it numerically. But I like to have a closed form formula for everything, and so every time we have a sub-Riemannian manifold, not sub. I don't say sub-Riemannian. A sub-manifold with an induced Riemannian metric. We cannot compute many things. That's why I didn't really investigate this direction.
Yep. Okay. Yeah, that certainly makes sense. Maybe another question is, so now, partly by your fault, actually, we have a big amount of possible geometries that we can put on the SPD manifold. And so if someone comes to that area, a user could be a bit puzzled to have a choice between so many possibilities. So I was wondering whether it's possible to somehow fix that by doing something like a decision trees that you could offer to users, asking a few questions and then to guide the users to the best geometry for their problem. Do you think that would be possible to do something like that? Do you have any idea what the first question would be in such a decision tree?
Questions, yeah. First, I think it's not my fault.
Partly your fault, I believe.
But maybe partially, but actually, I tried to give some principles to classify them and to understand, especially what are the differences between them. But they were quite, I think, almost all were already there. And so I think these principles. So maybe. I didn't want to present it on the slide because it was too small. But on page 25 in the manuscript, there is a tree, or it's not exactly a tree, but it's a graph. And I think that the questions of invariance are, I mean, when you say questions, you mean questions that the researcher could
yeah, I mean questions that would appear in the decision tree, so criteria against which you discriminate between the choice of various metrics.
Mm-hmm. So I think that all for example, the principles of invariance could help discriminate between several metrics. But it's true that, for example, they are almost all invariant and they're orthogonal transformations. And so if you look for a metric that is invariant and there is this group action, you are not very helped. So then, actually, in the applications, most of the time, it's either the affine invariant or the log Euclidean metric that are used, especially when we want to reject the rank deficient matrices to infinity. That's another criterion, actually. If we want the rank deficient matrices at finite or infinite distance. And so in applications, when we want the rank deficient matrices at finite distance, I saw that many people use what I call the Pure-Wasserstein distance, but you called it maybe a bit differently. It's also called Procrust. But so yeah, and they proved to be very efficient on the examples that were investigated. So we tried actually to for example, instead of a decision tree, we could, when we have a family of Riemannian metrics that is parameterized by, for example, 2 parameters, we could try to optimize the metric to fit it to some training data and then test them. And actually, we were retrieving kind of the metrics that are close to the log Euclidean metric or the affine invariant metric or the square root metric also. So I'm not sure that we could find questions in a decision tree, but I would say that so far the best alternatives seem to be the affine invariant, the log Euclidean, and the Dirac-Wahrscheinlichkeit matrix.
Okay, yeah, thanks. So indeed, maybe there is not a need for such a complicated tree because maybe you are realizing that in most applications, it's one of three principal metrics that seem to be doing the best jobs. Yeah.
Yeah, and the main difference between on one side the affine invariant log Euclidean and on the other side the Dirac-Wahrscheinlichkeit metric is the distance of the rank deficient matrices. But then actually it's quite an open question to understand why the affine invariant metric. So it's invariant under any affine reparametrization of the data set. And it's quite an open question to understand why it is the one that works the best when we want to reject the rank deficient matrices. So yeah, it's quite open.
Yeah, well, it has a long list of nice properties, as is Andolin Matthias properties.
Yeah,
maybe part of the answer, but yeah. Mr. Chairman, do I have time for a last quick question? Yes.
Quickly, yeah.
Okay, so in chapter 9, you have this very nice application of the theory of Riemannian orbit spaces. You can go very far in this SPD, in this set of covariance matrices. You want to go to correlation matrices, but what would come next?
Next, so there are many examples of orbit spaces. So for example, we can think of the eigenvalue multiplicity can be so on diagonal matrices, for example. First, we can see it as an orbit space, the orbit space of SPD matrices quotiented by the orthogonal group. And so the fact is that the stabilizer in the orthogonal group depends on the multiplicity of the eigenvalues.
Right.
So for example, if you have all distinct eigenvalues, you have only the choice of -1, 1 on each diagonal entry. But if you take the identity matrix, you have all the orthogonal group that is that stabilizes the matrix. So yes, so this is an orbit space that was actually studied partially, I think, in a paper in 17 from Wasser and colleagues, both on the diagonal matrices and the SPD matrices. So for example, I think that probably we could generalize this to positive semi-definite matrices. It was done only on SPD matrices. I think we can include in this framework the zero eigenvalues. I think it shouldn't be too difficult. And then I don't have other examples that come to my mind right now, but I think I mentioned
nice
some other examples in the conclusion of orbit spaces.
Okay.
Thank
you.
Thank
Thank
you.
you.
So we'll move to the second rapporteur, Marc Arnaudon, who is there in person. I don't know whether he should step
so let me take just 1 second to change the mic.
Okay.
So now I change. So could you speak again?
Does it work? Can you hear me?
Can you hear now?
Can you hear me?
Not very well, I must say.
From your mic.
I think it's worse with the mic of the computer. Maybe if you speak a bit louder.
Okay, is it okay now?
Yes, or I would suggest that you just speak next to Yann.
Okay.
What about that? But,
Here? Yeah, okay, so I changed the notification.
so that it's a real conversation.
Yeah, and actually you can also see Mark because
Exactly. Yeah.
Should I come here?
Please.
Okay, can you hear me now?
Yes, that's much better. Thank you.
I close the mic, yeah. Okay. But it does not work. No problem. So I'd like to say also that the manuscript is a very impressive work and very instructive and very pleasant to read, and it will certainly be a reference work for many people. So I like very much to read it. So I have several questions. My first question is very much related to the second question of Pierre of France. It's your fault. But it's more from a statistical point of view. I want to ask it more from a statistical point of view. What for performance of estimators, which metric to choose? For instance, we know that several examples, hyperbolic geometry helps for classification, for better results in classification. So do you have answer from a statistical point of view for improving the efficiency of estimators?
It's true that it's a field that I know a bit less. So I would say first that if we take only the affine invariant metric, the log Euclidean and the Biowa-Wasserstein metric, we can discriminate between the three with the curvature. The affine invariant metric has negative curvature, log Euclidean is flat, and Biowa-Wasserstein is positively curved. So probably changes things. I know that the curvature is very important in statistics and in statistical operations, but you work much more than me on this field. So it's the first element of answer. Then I don't know if we can say more things from a theoretical point of view. But another direction after this thesis is also to test all these metrics on data, and actually we started to do it with Taikeja Bala, who is an engineer working on the geomstats, and so he wanted to compare all the metrics from a data point of view. And so I think probably I didn't think about it before, but maybe we could integrate experiments from a statistical point of view in this comparison benchmark of all metrics and see what are the differences on statistical results.
So if you have continuous families with several parameters, you can imagine to make optimization of parameters with data on the performance of the classification.
And yeah, the performance of classification, I guess there is also performance of convergence, the speed of convergence, or we could test all these statistical parameters.
Okay. My second question concerns several constructions you made where you have the principal bundle, you have a group. Okay, you have a principal bundle on a group of isometry. You look at the quotient manifold, and you look at the geometry of the quotient manifold, the geodesics of the quotient manifold, and you say that there is when you project horizontal geodesic in the principal bundle, then you get geodesics of the manifold, and conversely, if you have geodesics in the base manifold, we can switch to the starting point is a principal bundle, so then there are horizontal trees. So my question is, in your examples of principal bundles, if you have a path in the principal bundle, are you able to write it as a product of horizontal path on the path in the book? There is a canonical decomposition. For instance, it's a correlation, correlation, which is SPD constituted by Diane. Can you make this?
So here, yes, because actually it's a bit false principal bundles because they are actually product manifolds. And so in this very example, we could easily have a horizontal part and a vertical part because it's only the projections to the manifolds. But I think it's not true in general.
It's not true in general.
Okay.
And in general, it's not easy, in fact. It's theoretically true that every path you can write it as a product of horizontal path on the path in the book.
But locally?
Or no, globally.
Globally.
Every split vector decomposed horizontally and vertically. And you can build your horizontal path. And okay. And in fact, it is very useful to find horizontal geodesics. So if you have any geodesic in the principal bundle, you decompose it as a horizontal path on the vertical path. You forget the vertical path, and you get a shorter path. And then you get two new points, and you build a new geodesic. You decompose again, and you get shorter and shorter paths. And at the end, you get horizontal geodesics. My question is, could you implement this kind of thing?
So I'm not sure to understand, but here I think, so you mean an algorithm to go from general geodesics to the horizontal ones in the principal bundle?
Yeah.
Okay.
Yeah.
So in the example of the quotient affine metric, we have the horizontal geodesics in closed form. So I would say that we already have them, and moreover, it's a product manifold. So I think in this manifold it's very easy. But then, for example, for the bureau search-time metric, it's also a quotient space, but it's not a manifold because the stabilizers have different are not diffeomorphic. And so here, I wonder if these types of algorithm you mentioned could be applied to these orbit spaces that are not bundles, but more general things than bundles. Do you see what I mean? Yeah. All the questions is how could we go from the manifold framework to the stratified framework? Is it still working? All the algorithms that we have in Riemannian manifolds, are they still working in orbit spaces? Maybe that's an interesting question, but I don't have the answer for now.
A short last question, but that is not the subject. What could you say about Finsler metrics?
I know the definition, but then so it's basically we replace the inner product by a norm. And so I think it also induces a distance on the manifold under certain assumptions, or
sorry,
does it
not symmetry?
Okay,
but you lose all stability, all symmetries. In fact, all invariance by groups.
Okay. Yeah, no, so then I really didn't study them, and I don't know how all these generalizes to finite metrics, because I don't really know the essence of these kinds of metrics. Okay, thank you. We cannot hear you, Rodolphe.
Yeah, thank you very much. We are now moving to the other members of the jury, and we will start with Professor Bhatia. And I would suggest that you also come forward and speak close to them.
If the other members want to hear what you're saying, it's probably
And please speak close to the microphone. Yeah,
yeah, maybe you can come here if you want to put your...
So that was a very beautifully prepared presentation. I enjoyed it a lot. While reading the thesis, I had some questions. Maybe I didn't understand a few things. So we have to go to page numbers. Can we do that?
Yes.
absolutely.
So page 24, you seem to say GLN, you are reducing to SLN into positive. Is that right, or am I reading it wrong?
Yes. So
I'm slightly puzzled. If you factor out SLN, you should get all real numbers. So what is the mystery here?
the mystery here is that actually we are talking about metrics that are invariant under these two groups, these group actions, and actually all the GLN invariant metrics are GL plus and invariant metrics, but the converse is also true. And so that's why with R plus and SLN, we can reconvert GL plus. And then since the metric is GL plus invariant, it is GLN invariant.
And how about the ON? You get positive diagonal only, or?
Sorry?
GLN modulo ON. This would suggest it's a positive diagonal matrix. Is that right? Or again?
No, here I'm really talking about families that are invariant under these group actions. So I'm not talking about the groups itself themselves. So, but I agree with you that it's actually the GL plus that for the first pair. For the second pair, the orthogonal group and the positive diagonal group, it generates the GLN. But if your question was if we quotient GLN by the orthogonal group,
should get positive matrices, right?
Yes.
Okay, chapter 2, now there is a lot of literature which you seem to have ignored. For example, there are lots of papers by Chandler Davis, direct rotations of subspaces, and work of French mathematicians, in fact, Jordan and others which he quotes. So you should take that into
No, I completely agree that in the chapter 2, I was trying to get some results that I needed for later. And I tried to go into this literature that I didn't really know. So I cite some words, but yeah, I must have forgotten many of them.
Yeah, just to point that out. Now, page 47, definition 3.1. It's I don't understand it. You say a module is a vector space W on which G acts continuously, such as what?
Such as V. So the V is the one I introduced at the beginning of the section, but maybe it's not clear said like this. I wanted to say that the V that is defined here is an example of a module, but
yeah. So this sentence, first of all, doesn't make it doesn't have any meaning in English.
Okay.
Maybe you're translating something in French.
Okay.
But modules and vector spaces are different, right?
Yes.
So you start by saying a module is a vector space. I think something is not quite correct here.
Actually, it was I read some literature where the vector spaces on which there is a group action are called G-modules. So maybe
so vector spaces are always over fields, and modules need not have fields as the underlying scalars, so to say. So there's a difference.
Okay. But yeah, I'm talking about a different thing here. So yeah, okay, there is a misnaming maybe, but I wanted to find a very simple name to have the vector spaces on which a group acts, and yes, I decided
this needs correction, I think.
Okay.
Chapter 3, I was really puzzled. Does representation theory really help here, or is it just complicating things? I wasn't sure. So could you tell us?
So actually, the way I came into this was when I looked for all the permutation invariant inner products on matrices, on spaces of square matrices. And then I was asked the same question for the block orthogonal invariants. And I found that actually we could find a general way of deriving all the inner products that are invariant under a certain group. And that's why I formalized all this with the representation theory. I found it helping, at least for me. But maybe it's not.
To me, it seemed to complicate things rather than simplify.
Okay.
Yeah. Okay. Page 70, again, I have a serious difficulty.
Mm-hmm.
You have two positive definite matrices, sigma and lambda.
Yes.
You are taking their product,
mm-hmm,
and then a square root.
Mm-hmm.
What does that mean? That product is not positive definite. And you seem to suggest it's positive definite.
No, so so actually it's simply a notation that is explained a bit later. I mean, on the same line. So actually, this sigma lambda is congruent to.
Not congruent.
Well, not congruent. Sorry.
Congruent
similar.
would preserve positivity. So
yeah, it's similar. Sorry, it's similar to an SPD matrix, and so the square root is defined as we apply the similarity, we take the square root, and we apply the similarity back.
So this needs correction. The way it's written.
It's written in many papers like this, actually.
Okay, I'm sorry then.
So that's why I took it. But it's true that at first read, I was confused when I.
Yeah, very often they will write like, you know, every matrix with positive eigenvalues
mm-hmm,
has a square root with positive eigenvalues.
Yes.
So maybe. All right. Now, chapter 4. Here I have a question which you might like to think about.
Mm-hmm.
You characterize these ON invariant inner products
mm-hmm,
as alpha trace x squared
mm-hmm,
plus beta times the square of trace x, right?
Yeah. So sorry, which page?
Trace, general, just chapter 4.
Okay.
So alpha, so there is a term involving trace of the square of x,
mm-hmm,
and another term, the square of trace x.
mm-hmm, mm-hmm.
So one should notice that the first one is the sum of squares of singular values,
mm-hmm,
and the second one is the square of the sum of eigenvalues. Mm-hmm. Is there any philosophy behind this, that every such inner product should depend only on singular values and eigenvalues and nothing else?
So these are the products that are invariant under orthogonal transformations, and so.
No, the first one singular values, and second one involving eigenvalues. See, in matrix analysis, there are unitarily invariant norms and then weakly unitarily invariant norms. So you seem to be getting a mixture of the two. But is there any explanation that these are the only two terms which should come up?
But here we are talking about symmetric matrices, aren't we?
Yeah. But nevertheless, the symmetric matrices, the singular values are just the absolute values of the eigenvalues.
Yeah.
But I'm curious, why should only these two things occur? See, like von Neumann has a theorem about unitarily invariant norms must depend only on singular values. So that's the first thing he proves.
But here the eigenvalues and the singular values.
Yeah. My question is that have you thought about why should only these two things occur and nothing else? I think it's something which needs a little thinking and explanation. That any ON invariant inner product
on symmetric
matrices should be a function only of singular values and eigenvalues.
Yeah, I didn't phrase it like this, but it's
okay. Now you say in page 83 that the use of co-metric has been very helpful in computations. Any examples you have done? It didn't seem to say that. So just a question here.
Here it's really based on the fact that in GeoStats we implemented, and I didn't do it myself, but it is implemented like this by integrating the Hamiltonian flow, and it requires the co-metric.
So co-metric has been helpful. The examples were not given, so I was just curious. And two general questions. Everything you say is about real symmetric positive. What's the problem in going to complex matrices? Everything should work.
It's true that it's a very interesting direction that I didn't investigate because I started on SPD matrices, and so yeah, I would like to.
Because almost everything you are doing,
I think most of what I did can be generalized to complex matrices.
Now, chapter 9, you seem to suggest that the reason for introducing Bose-Wasserstein distance is simply that it can be defined over all positive semi-definite matrices.
The reason?
For introducing the, I think that's not quite right. There are intrinsic reasons for that metric, optimal transport, quantum information. The way you have phrased your introduction, it seems to say that the affine invariant metric doesn't work for lower rank matrices, and this one does. I don't think that's
the main reason for the introduction. Probably.
So it's a little amusing. And having introduced all these metrics, just one thing which links with what Mark was saying earlier, Finsler metric. You are talking on page 170 of length space. I think already you are talking of Finsler metrics there, because what's a length space? Can you explain?
Yeah, so a length space is a space where, so on a metric space, we can define the intrinsic metric, which is the metric that measures the length of paths. And if it coincides with the initial distance metric, the space is called a length.
Yeah, so you are saying that there is a curve which is not a straight line, but whose length is the same as that of the straight line. Right? Is that what you're saying?
So, for example, we can take the sphere. If we consider the embedding distance, the Euclidean distance, and then if we consider the distance induced by the paths, they are different.
Yes.
And so they don't coincide.
Yes. So that's exactly what I'm saying. So length space in your definition means there is something which is a geodesic, not a straight line, whose length is the same as that of the straight line. Is that your definition of length space?
So maybe I should have a look.
Okay, I just want to make a comment that in the interest of time, that you seem to be talking of a space in which there is a curve embedded in a Euclidean space. There is a curve which is not a straight line, but its length is the same as that of the straight line joining the endpoint. Is that your definition?
No, it's not my definition, definitely, but maybe it's...
That's the impression I got from what you say about length space.
Okay.
And I just want to say that what Mark asked, I mean, that would not be possible in Riemannian geometry. It has to be Finsler geometry. Any good examples of such a space that you looked at?
A length space?
Yes.
So any Riemannian manifold is a length space?
Now that's what's confusing me, because so take this sphere, the geodesic joining any 2 points. will not have the same length as that of the straight line joining the endpoints, right?
Yeah, it depends on which metric you put on your
usual metric. So any Riemannian manifold is not a length space according to what I understood.
So if you take a Riemannian manifold and take the Riemannian distance on it, this Riemannian distance is intrinsic because it measures the length of path, and so the space is a length space. That's the
so I have to understand the definition. Yeah.
So yeah, maybe I need to clarify the definition.
Okay, last question. So, having defined so many metrics, have you computed any Fréchet means and so on?
So many Fréchet means were computed for the usual ones, so the affine invariant metric like Euclidean search time. Then we tried to compute Fréchet means and other components numerically for the mixed power Euclidean metrics. And so, yeah,
you have some.
Yeah, we computed some, but it didn't give better classification results than
explicit formulas or
no, not explicit formulas.
Okay, thank you.
Thank you.
Thank you for the clarifications.
Thank you very much, Professor Atia. We move now to Professor Willing Lay. Will you also please come forward?
Okay, can you hear me? Okay, so hope is okay. Okay, I will ask probably a try not to use page, but I might need to tell you which page it is. First question is about you, after you calculate the power transport on the Euclidean versus Stein metric, when you communicate it, it resembles to the one on the pendulum takes place. My question is, do you think it's just coincidence or is there any reason behind it?
That's a question that we tried to investigate with Elodie. So actually, the Dürr-Wasserstein space is the quotient of square matrices by the orthogonal group, which is quite close to the definition of Kendall-shaped spaces, even if there are some other normalizations in the definition, if I'm correct. And so I probably the two formulae, there is a reason behind, but we were not able to understand properly where the coincidence comes from, because there are also some differences between the two equations. So it's not very clear why.
Okay. The next question, still linked to same space, and you mentioned applicated geodesic equations always have a cut time. In a lot of cases, it is finite cut time. Have you looked at the case? What happened when you approach this cut point, the cut time?
You mean
so what happened at the cut time?
So, for example, for the Dürr-Wasserstein metric, in SPD matrices, the cut time is actually the time when the geodesic leaves the space, so when it hits the boundary. And in low rank matrices, fixed rank K, it depends on the matrix you are looking at. So sometimes it is when it reaches a more singular stratum, and sometimes it's not the case. Sometimes even, and it was proved by Estelle Massa and Pierre-Antoine Rossi that some geodesics in lower strata are goes to infinity. Not the cut time, but the geodesic can be defined on R, on the whole real numbers. Okay. But of course there is a cut time. Yeah. But I mean that sometimes the cut time is not on the lower stratum. It could be also in really a point in the space.
Oh, that is just not something I expected. Okay, so it's not always tends to the low, tends to the boundary. So.
Sometimes yes, sometimes no. Yeah, yeah. On SPD, it's always the case, and on lower rank matrices, it's not always the case.
And I suppose probably I expect the answer you will say is no. Now the question is, I'm talking about the full rank case.
Mm-hmm.
So when have you looked at the case? What happened when approach it? Have you looked about curvature, for example?
So I didn't do it, but Rajendra in his paper on the Gervais-Stein metric, I think it's quite clear. It's also related to the work of Takatsu in 2010, 2011. And so actually the curvature goes to infinity on the boundary. It's simply because in the formula of the curvature, there are two eigenvalues involved at the denominator, and so when you reach the boundary, it's the two lower eigenvalues, and they go to 0, and so the curvature goes to infinity. It's proved in the literature that, and it's true also in each other stratum, that the curvature goes to infinity when you go to lower stratum.
I would expect that there's two both cases.
Sorry?
I expect it is possible time to infinity and possibly it's not time to infinity. Anyway, that's my.
So another discussion that we had with Xavier is that probably because this is the sectional curvature, but probably there are some directions where the curvature stays finite and remains finite, and the direction where it goes to the boundary, probably here it becomes infinite. But there is a curvature in the stratum that is finite, so there must be a continuity between the two curvatures.
Okay, now come back to the question linked to the orbit space. Okay. And I look at a table you had, looks at all possibilities about the number of geodesics which come to points. For all except one, or other cases, either have unique geodesics or have infinity. But in the one case, you have two. Can you tell me why? Do you have a view why that is different?
So I have a mathematical reason, but I don't have a philosophical reason. So mathematically, it comes, and actually it was almost proved in Estelle and Quentin's work. The degree of freedom is the orthogonal group of dimension 1, because it is the case where the rank of the product is only one lower than the rank of the two matrices. So the free part is the orthogonal group of dimension 1, which is only -1 and 1, the set -1 and 1. And so the set of all minimizing geodesics between the points is parameterized by -1, 1. So there are two geodesics. But then it only comes from the structure of the orthogonal group in dimension 1. And in higher dimensions, the group is infinite, and so there's an infinite number. But,
that's something I need to know about it. Okay, that's the very last question. Again, it's about your comment. When you talk about the space of the correlation matrices, and when you look at the quotient matrix, right after you talked about, you quote existence of a logarithm map. Probably I will call the existence of geodesic values different to that. So you see, indicates that you can't. What you said is that you're still unable to prove whether the O is unique.
Okay.
So does that? I appreciate that there's always a possibility. So my question is, do you expect non-uniqueness in this case? Or you have some experiments or something?
No, I was not able to have a clue from the experiments. Sometimes I thought it should be unique, and sometimes I thought it should not be. So I'm really lost in this question.
No, I doesn't look you.
Actually, so maybe an element that goes against the uniqueness is that the positive character. And so probably at some places, if you go too far, there must be cases where it is not unique. But I didn't prove it.
Okay, just not any more questions.
Thank you.
Thank you very much. We'll now move back to the members who are online and continuing with Frank Nielsen.
Okay, so thank you. First of all, I think it's very impressive and inspiring work that you presented today. And I would like to congratulate you for the clarity of your presentation. I mean, I had some hard times sometimes in the manuscript because it was quite heavy reading with quite heavy mathematics somehow. That took time for me to read. But today, your presentation shows a very clear picture and also a very good panorama of all your work. I have followed for over 3 years, so I'm very pleased to see the outcome that happened in the last, say, 18 months. It's very amazing. So this is what I wanted to say first before the question. So I have 3 questions, and it's a high-level question. The first question is about the motivation. If the motivation is to find a dissimilarity, do we need to have a Riemannian distance with a triangle inequality or not? Or can we work at a higher level, like the divergence level? You talk about alpha-beta divergence, for example. And once we have a divergence, we can induce a Riemannian metric and connection, like with Eguchi methods, for example. So my question is the following. When is triangle inequality nice in application, and when is it harmful?
Mm-hmm. It's true that I didn't think this way the necessity of Riemannian geometry. I thought it more for the Riemannian metric than for the distance that is induced, because the Riemannian, from what I read, I know that the Riemannian metric helps to do many operations on the manifold, and it seems to me that the divergence, the dissimilarity measure is a bit more limited, but maybe I'm wrong.
If you can allow me to ask one more tiny question in that question, is that, for example, can you try to reconstruct some divergence? Let's say, for example, we have F divergence, which are very useful for multivariate normal distribution, so that the induced Riemannian metric from that F divergence is the metric that you study.
Mm-hmm.
For example, for the mixed power client, you got this alpha beta as one realization. For the other metrics, can you try to go uphill and get some divergences which realize the metrics, for example?
So I was only able to do it for the mixed power Euclidean metrics. For example, I tried for the Biot-Wasserstein metric, but I didn't manage to. So. But when we have a Riemannian metric, we have the distance that would serve as a dissimilarity measure, and so your question is what do we have on distances that we don't have with divergences?
For example, if we take the Fischer-Rao distance of multivariate normals, we don't have the distance, right? We have a geodesic equation, but we don't have closed form formulae, right?
With the mean, with the non-null mean, you mean?
Oh, okay. Yeah.
Or,
Sorry. So it's a bit different. Yeah. You're right.
But no. But well, it's true that we have the formula for the Fisher-Rao metric on SPD matrices. But then, no, to be honest, I don't know exactly what I think the triangle inequality is useful in some algorithms, but I don't know more about.
For nearest neighbor queries, you can prune, for example, for pruning technique in data structures or query location. Maybe it's useful, but yeah, it's just one high-level question I wanted to ask. The second one is also very high level. You mentioned precision matrix and covariance matrix, and actually the space that you study is semi-positive definite matrices, right? So on the OpenCon, you have a perfect bijection, and the parameterization are interchangeable. But if you take precision matrices with rank deficient, then it is covariant matrices with infinite eigenvalues. So my question is that, do you think it's a good question to look at the compactification of the cone, where you can both have a zero and infinite eigenvalues somehow?
Yeah, it should be a very nice idea. I didn't really think about it before, but I think that when we take the pseudo inverse of the covariance matrix, we keep the null eigenvalues to 0, and so we could also study the space with a 0 and with the not infinity instead of a 0. So you mean if we compactify, we can actually invert in this compactified cone, and so then we can.
So it's kind of having a double cone model, one cone for the precision and one cone for the covariance.
Yeah, I remember that you sent it to me.
I think this is very intriguing, very intriguing. And it's related to parameterization. When you map the eigenvalue into interval 0, 1 on a closed interval 0, 1, right?
Yeah, I don't remember exactly how it's built, this double cone, but yeah, probably the geometry is completely different. For example, I don't know how to generalize the affine invariant metric to the compact to the compactified cone, and then I guess the geometries on the double cone are completely different from the ones I mentioned today, aren't they?
I mean, the paper I'm referring is a whole paper by James, and very not so much known. And but I think there's a lot of perspective in that paper actually. Okay, so my last question is more about application, because so you have metrics on SPD cone, you have metrics on the elliptop, and for example, you could try to look at interplay of the cone with the elliptop by projection, like from finding the closest correlation matrix, for example, and to look at all those Riemannian metrics for defining projection and have properties, for example. Did you try to look at that, or?
So not yet. I didn't try actually. I didn't try because so far I only studied the space of full rank correlation matrices. And I saw that in these applications where we need the projection, of course, the projection belongs to the boundary. And so there is a null eigenvalue. So, but probably for the next steps of, when we study a geometry for the whole elliptope, the closed elliptope, then it should be very interesting to look at these applications.
Okay, I have many questions, but I will stop here for the sake of time. But congratulations again for this very interesting piece of work.
Thank you.
Thank you very much, Frank. So we move to Min.
Thank you very much for the spectacular presentation, and congratulations on the great thesis. It's a lot of amazing. The results are really amazing, and it's a great body of work. So congratulations. So I just have some questions. Actually, some questions were already asked by other members. Actually, so I will keep my questions actually quite short. So there was this question about this. So you have you kind of trying to have this unification of the different matrix, right? And then suddenly we have like kind of started from a couple of years ago. There was this like Cholesky and log Cholesky matrix and so on. So do you think like these can fit into somehow like a bigger framework?
Fit in what?
This is like a bigger framework, because you have like this kind of like mixed power. Like, do you think this you can have kind of fit this like log Cholesky kind of matrix into a bigger framework?
Yes, I remember our discussions on finding the global frameworks for integrating your alpha proposed metrics and our mixed power Euclidean, etc. Something I didn't mention is first, I think what's interesting is to find the smallest family with few parameters, such that there are some principles behind the metrics that are in the family. And actually, if we take the cometrics of the mixed power Euclidean metrics, this includes the Biot-Wasserstein metric, because the coefficient in the Biot-Wasserstein metric is 1 over di plus dj if you write it in diagonal at a diagonal point. And if you inverse this, you get a metric that is in the family of mixed power Euclidean metrics. So actually, if we take the mixed power Euclidean metrics and their cometrics, here we can include the Biot-Wasserstein metric. So then that's why also at some point I stopped to try to find some families of Riemannian metrics that because I thought it was enough with this classification. These Cholesky metrics, they are not invariant under anything I tried at least, and so I don't know exactly how they could fit in a bigger framework, but I'm not sure we need it actually. That's why I didn't investigate this more.
I think it could be. I think it could be interesting from a numerical viewpoint to see how they work actually, because I think because the Cholesky decomposition is kind of numerically stable, right? So I'm kind of curious actually how they work on via data actually, because it's also it's also kind of it's actually kind of interesting somehow. It's from a mathematical viewpoint, it's interesting, and it's some
No, I'm sorry. Something I didn't try, but I think that between the variance, the various Cholesky based metrics on SPD matrices, probably if we do a similar operation than what we did on the Procrust or fine invariant, if we put a power transformation of the Cholesky metric, probably we could reach the log Cholesky metric, or
I think we can do that. Yeah, we can do like the power, and then we can reach it, because actually it's actually well defined, because it's because all the eigenvalues all the diagonal elements are positive.
Yeah, and the space of triangular matrices is stable by all these power operations, so probably we could do this, but.
So the second one is more like a command actually. So we like in machine learning, we care a lot about like defining like a positive definite kernel, especially Gaussian kernel with these distances. And so, for example, like the affine invariant metric has more kind of invariant, like it has some more invariant properties. And then with the Euclidean metric, for example, has like fewer invariant. So it's still like fewer invariant properties. But that because it's flat. And so we can define like Gaussian kernel on using it. Actually, so like we can define Gaussian kernel and also polynomial kernels. And so it's also like one consideration as well. So not just like not only kind of the invariance properties actually. So we also care about these things. So like defining a positive definite kernel using it. So this kind of also like kind of related to the questions that Pierre Antoine was asking before. So another thing from the machine learning viewpoint is actually positive definite kernel. We would like to define a Gaussian kernel using these distances.
You mean that it could be another principle to find interesting?
I think it could be. I think it could be like it could be useful to point out, like, because actually for people in machine learning, we are like kind of, if you look at the various application in machine learning, actually people actually use the log Euclidean metric, because actually for the affine metric we use the distance, right? That's just only the distance. But then for the log Euclidean metric, you can define a kernel as well, so you can have like kernel methods. So it's another actually feature. It's actually another feature that's actually useful for people in machine learning, computer vision. Actually, we actually use this. We actually use it actually. So now, so another question is on the this log scaling with the log scaling metric with the for the correlation matrices. So is this log operation explicit? Is it like, does it have a closed form formula? Is it explicit?
So in one direction, yes. In the other direction, not. So if you take this row zero space, the space of symmetric matrices with null row sums, if you take the exponential of this matrix and then the correlation, if you normalize by the diagonal, you get a correlation matrix. And this is a bijective parametrization of correlation matrices. Yeah, it's true that I didn't mention that the converse operation, the inverse diffeomorphism, is not known in closed form, but actually we can compute it very efficiently. In the manuscript, I propose an algorithm because I wanted to have at least one, but actually I think there are other methods to compute these scaling. That is, there is a huge literature on this scaling operation. And so I found some references where they know how to compute this scaling very efficiently.
And so you can define also like a positive definite kernel using this distance, right? With this okay, good. So for the log Euclidean metric, actually for the SPD metric, it turns the SPD matrix into like a set of SPD matrices into a vector space, not just like it's like a vector space. So like it turns into an inner product space actually. So is it the same thing with this log scaling operation for the correlation?
Yeah, that's why. That's why I call them all log Euclidean metrics, because actually they all go bijectively to a vector space, and so you can define all the kernels you want. But no, it's true that I didn't think about this application.
Okay, so another question is actually related to what Professor Baccia was asking as well, the Fréchet mean at the very center. So for the Borel versus Stein distance, actually, so this is defined for everything, for like all the covariance matrices that are singular or not, right? But currently we have a barycenter equation, the kind of fixed point equation for pairing the barycenter with the Borel versus Stein distance. But this equation is actually not valid for the singular setting because it's actually this equation has been known for a very long time, but it's actually explicit the case when for the non-singular setting, because the proof of existence and uniqueness depends on the fact that everything is actually strictly positive. And also the fixed point equation itself, it actually has infinitely many singular fixed points. So it's actually it actually cannot be used in the case when the barycenter, for example, is singular. So I'm not quite sure whether like how much is actually, whether you have kind of thought about this barycenter question of barycenter much, especially for, in the case of the Borel versus Stein distance, you have like a one whole chapter in the end with the covariance matrix of like different ranks and so on. I'm not quite sure whether you have actually thought about these questions of Fréchet means.
This barycentric equation, why is it ill-posed for PhD?
Oh, because it actually has, for example, it has 0 as the fixed point. It can be shown that it has infinitely many singular fixed points. Fixed points which are singular matrices, and so it's not suitable for finding the fixed point when the fixed if the barycenter, for example, is singular. then it's actually it's not suitable. Maybe I will maybe I will talk to you maybe after this.
Of course,
I can discuss with you after this in detail.
When you say barycentric equation, you mean the equation to find the barycenter or the Fréchet mean of
yeah
set of matrices. I think that in each stratum, so if you know the rank of your matrices, I guess that the equation should be well posed because you are in a manifold. So actually, it's from the work of Estelle and Pierre-Antoine. When you are in this manifold, you can lift everything, and I don't see where the singularity would make a problem. Then it's true that between matrices of different ranks, there I don't.
I should remember. We can talk about this later. Actually, I would actually we can talk about this in. Okay. So my one final comment is actually on chapter 8. I think it's I think the presentation could be improved because as I said, according to as I agree with what Pierre was writing on his report, that it's a bit confusing because when you were talking about the different conjectures and so on. It was a bit confusing to read, but otherwise, like the whole thesis is great. It's like the results are really great. And thank you for the presentation and all the results. Thanks a lot. That's all for me.
Thank you.
Min. So it comes to me, I think that we've been asking you questions already for 90 minutes. So I'll cut down my time. I'll just ask one maybe very naive question, but as an engineer, I like to think of positive definite matrices as, matrix generalizations of positive numbers, and I tend to associate those to hyperbolic geometries. And so when you discuss that many of those metrics have, not constant sign curvature, I'd like to ask, is this a sufficient criterion to reject those metrics? Or, I mean, could we consider this as sort of artifacts of the construction? Or would you defend that sometimes it makes sense to have such sort of complex curvatures? And in that case, would there be any interpretation?
I think that's not a naive question. No, on the contrary, it's quite a deep question that my observation on the curvature was that when the curvature is constant, we have some tools to compute on the manifold, and we have nice results of existence and consistency, etc. So every time I see non-constant sign curvature, I'm a bit afraid of this geometry. Then the point is also that the geometry should fit the application, and so if for certain reasons in an application we want to be able to compute I don't know why, but to have negative curvature somewhere, positive curvature elsewhere, it could be interesting. But the other point, for example, for the quotient affine metric, is that it's very difficult to see where is the negative curvature, where is the positive curvature. I was able to show that in some directions it goes to infinity, but actually it was quite difficult to find this direction. So yeah, I would say that it's a bit dangerous, but if you want to go there, why not?
Okay, thank you very much. So I will give the final words to the advisor. So Xavier, if you want to maybe come forward and ask your questions or.
Yeah, thank you very much, Mr. President. So yeah, after all this time, I think I don't have questions. I just have a few things maybe to say and to stress. First, I want to start with a bit of history. We were talking at lunch that we met 5 years ago during your gap year at the École Centrale Paris. And I remember that at that time you were already deeply involved in teaching not only mathematics to people who have programming mathematics, but organizing the courses at École Centrale. At that time, it was not very clear for you that research would be an interesting track. And after a year and a half of discussion, I was glad that you decided finally to make a PhD. And now I'm even more impressed because I had the impression to throw away a few seeds for your research. And then now you grew out of that a real forest where maybe you are the only one to know the whole thing. And I have to admit that scientifically, I can't say anything. You have a view which is much deeper and much wider than the one I have now on this topic. So maybe just a few other points that I want to stress. One of them is that when you arrived, this was corresponding with the start of the geostatistics ERC project. And you were really instrumental in actually building and creating the team spirit by discussing with everyone, welcoming everyone. I think everybody in the team was welcomed by you and felt nicely welcome. So that's really something very important for which I want to thank you. Your human qualities made it really a dream to collaborate with you, and I want to say that it's really in that way that I'm seeing it. It's not the other way. Yeah, so in conclusion, I want to say, well, that I really liked the time we spent together. I hope you liked it as well. And I would like to wish you a brilliant journey into your future academic career. Thank you.
Thank you very much. So Yann, I think that now the jury will want to have a private discussion. So I would suggest that we stop the live streaming.
Yes.
And then maybe I will ask you to leave the room and I suppose there will be a way to hold you back.
So just one word for people online. We are going to come back in a while. Peut-être en français parce que je pense qu'il y a plus de gens qui suivent en français qu'en anglais. Donc on revient dans 20-30 minutes grand maximum. Donc restez en ligne et on va couper la diffusion et on revient. Merci, à tout à l'heure. C'est bon? Attends, je remets le... Là, c'est bon? Peut-être je remets la caméra. Oui, alors Rodolphe, on est de nouveau sur YouTube et donc je crois que c'est à toi. Mais tu as le micro coupé.
Okay, excellent. So I will just read the report that the jury wrote after your presentations and your answers to the questions. So we found that you gave a particularly inspiring and comprehensive presentation of your work, and that you succeeded to highlight the main contribution of the dissertation in a style that struck a remarkable balance between pedagogy and mathematical rigor. We found that your presentation was very well structured and were impressed by the quality of the slides that contained very insightful illustrations. And you were able to convey quite abstract geometric concepts to a general audience, which is certainly not easy. The answer to the questions demonstrated your deep understanding of the concepts and also your ability to relate your own work to the bigger picture. So overall, the jury was unanimously impressed by the quantity and the quality of the novel results. We think that the dissertation is likely to become a major reference on the geometry of covariance and correlation matrices. It paves the way to further investigations of both theoretical and practical nature. Hence, the results, the presentation, and the answer to the questions all suggest that you're highly promising researchers with excellent pedagogical skills. And for all these reasons, the jury wants to award you the title of Doctor of Université Côte d'Azur, and we all wish to sincerely congratulate you. And so a big applause. I'm only sorry not to be there in person to shake your hands.
Sorry, Rodolphe, we couldn't hear what you said in the end.
I'm only sorry that I'm not there in person to shake hands.
Yeah, thank you. Thank you very much for that's the most difficult part, probably. So yeah, I would like to thank all the jury members, and so Rodolphe for being the president of the jury, Marc and Pierre-Antoine for your very interesting comments in the reports. I'm sure it will help me improve the manuscript again. I would like to thank also Rajendra Bhatia and Quy Linh Le, especially for coming also, and for your very interesting questions, and I think our nice discussion. I would like to thank Min and Frank for also the nice discussions. And yeah, maybe Frank, I would like to thank you particularly because you followed me during all the thesis and gave me many references and advice. So thank you. I would like to thank my supervisor, Xavier. So I'm not sure I'm able to do it in English, so I will turn to French to be able to express my gratitude. Donc, merci beaucoup, Xavier. J'ai vraiment découvert un champ de recherche et puis comment dire, une façon de travailler, enfin, le monde de la recherche, en fait, grâce à toi, que je ne connaissais pas du tout. Et j'ai beaucoup apprécié ta façon d'encadrer qui se met à la bonne distance entre le suivi très attentif et attentionné de mon travail et de mon parcours, et en même temps de m'avoir laissé la liberté de choix, de recherche. J'ai beaucoup apprécié cette attitude bienveillante et qui laisse s'exprimer ce que j'ai voulu faire dans la thèse, et c'est tout l'environnement que tu as créé dans l'équipe, et notamment avec Gistat aussi. Donc au début, il y avait juste Nicolas et moi, et c'était déjà des échanges très riches. Et puis ensuite, c'est un peu comme les métriques, ça a pris une ampleur beaucoup plus grande, et ça a permis de comprendre plein d'autres choses aussi, et donc ces interactions. Puis tu nous as emmenés un peu partout aussi avant le Covid. Donc voilà, pour tout l'univers que tu as créé autour de ma thèse, en tout cas dans laquelle j'ai pu baigner, et pour toutes tes qualités d'encadrement, vraiment, merci beaucoup. Voilà. Maintenant, alors je voulais remercier plein de monde. D'ailleurs, j'avais écrit une petite note pour pas trop oublier. Déjà, donc je voulais remercier Isabelle pour son travail sur le travail administratif tout au long de la thèse qui a été vraiment important avec tous les voyages, enfin, tout ce qu'on a fait. Je voulais remercier aussi Nicolas, parce que c'est par lui, Nicolas Ayache d'abord, parce que c'est par lui que tout a commencé. C'est voilà, quand j'avais écrit un message, et puis après mon CV a circulé, et puis on parlait ce midi des hasards qui forment un peu. Enfin, je ne vais pas faire le sketch d'Otis, mais mais donc, je voulais remercier aussi Marco, qui était aussi dans mon comité de suivi et qui m'a donné beaucoup de très bons conseils. Donc, Maxime, Hervé et Irène aussi de l'équipe. Je voulais remercier particulièrement l'équipe GStat. Alors, entre G-Statistics et Geomstat. Et donc, particulièrement Nicolas, voilà. Parce qu'on a passé un bon bout de temps à travailler que tous les deux. Je pense on a compris beaucoup de choses ensemble. Et puis même après, tu m'as beaucoup aidé sur toute la partie pratique. Voilà, j'ai toujours apprécié nos échanges, que ce soit scientifiques ou en dehors de l'INRIA. Je voulais remercier Nina aussi parce que donc je ne sais pas si elle suit, mais le fait d'avoir cette librairie Geomstat, ça nous a vraiment permis, enfin en tout cas moi qui ne suis pas très à l'aise là-dedans, ça m'a permis de rentrer beaucoup plus facilement dedans. Et puis je voulais remercier, je ne sais pas si je me lance dans des citations parce que je risque d'oublier des gens, mais en tout cas tout GStat. Voilà, je voulais remercier tout et Pion aussi, qui m'a beaucoup aidé, notamment sur la présentation, qui ont vu les phases de construction. Et donc, c'est beaucoup grâce à eux aussi que j'espère que la pédagogie de la présentation s'est améliorée. Et je voulais particulièrement remercier Clément, Selma, Santi, Jauma, Luigi, avec qui j'ai eu de très, très bons moments aussi pendant la thèse. Et c'était important pour souffler et pour avancer aussi. Enfin, ça va ensemble. Voilà, je voulais remercier Paul et Lauriane qui sont venus exprès de Paris pour la thèse, enfin la soutenance. Et puis tous mes amis qui suivent en ligne, qui malheureusement n'ont pas pu venir, mais qui m'ont beaucoup soutenu pendant tout ce... Et je veux vraiment insister là-dessus parce qu'il y a des moments qui sont assez noirs en fait pendant la thèse, et il y a toujours des gens, des amis qui sont là, et c'est vraiment fondamental. Voilà, et je voulais remercier toute ma famille. Alors, comme j'ai main moite, en fait, j'arrive pas à allumer mon téléphone. Donc, parce que je voulais saluer ma famille d'un peu partout. Alors, du coup, je voulais saluer Tunis, Montpellier, Toulouse, Cahors, Paris, la Martinique, New York, Singapour, la Serbie, et peut-être Londres et Los Angeles aussi. Donc, ça m'évite aussi de citer tout le monde. Voilà, je voulais remercier Radomir d'être venu en special guest. J'apprécie beaucoup ta présence. Je voulais remercier, ça ressemble à un discours des Césars, mais là aussi, je pense que, enfin, en tout cas, moi, je mesure l'importance de personnes comme John, Eric, Michel, Thierry, qui sont des mentors pour moi, qui m'ont beaucoup accompagné et conseillé, aidé. Je voulais particulièrement remercier mes parents qui sont là, qui sont venus aussi, et qui m'ont toujours accompagné, soutenu, et puis depuis beaucoup plus longtemps que la thèse. Et évidemment, je voulais remercier Sarah d'être à mes côtés. Et je sais qu'il y a eu des moments assez difficiles aussi. Et donc, enfin, il n'y a pas que des moments difficiles d'ailleurs, il y a eu des moments géniaux aussi. Et donc, je voulais te remercier d'être là avec moi. Voilà, donc il y a un pot de thèse tout de suite. Et à 18 h, je vous invite tous à la plage à Jean-le-Pin pour fêter ça plutôt dans la bonne humeur et dans le soulagement. Voilà. Merci beaucoup.
Thank you very much. So we will close the Zoom and we wish you a happy celebration.
Thank you, Rodolphe. And I hope to meet you at some point elsewhere.
Definitely.
Thank you.
Bye-bye.
Okay. Thank you.
Bye-bye. See you.
Bye-bye.
Bye-bye. Bye-bye.